Dear students, now I want to discuss hyperconjugation. It is very important concept. Other names of hyperconjugation. No bond resonancy. Another name, Baker-Northern effect. Another name, antichimeric effect. Okay, these three are the other names of hyperconjugation. Now, in hyperconjugation, which group involved in this effect? For exhibiting hyperconjugation, sp3 hybridized carbon containing hydrogen involved in CH sigma bonded electrons donated to adjacent vacant or deficient sp2 hybridized carbon. Here sp3 hybridized carbon containing hydrogen, these sigma bonded electrons delocalized with deficient sp2 hybridized carbon. So this is mandatory. You know, sp2 hybridized carbon, adjacent carbon, if it is sp3, then that sp3 carbon only called alpha carbon. Understood? sp2 hybridized carbon, adjacent carbon, if it is sp3 carbon, that carbon is called alpha carbon. On that alpha carbon, at the alpha carbon, at least one hydrogen is there. That CH sigma bonded electrons can stabilize the adjacent sp2 hybridized carbon. This part is mandatory for hyperconjugation. This part is mandatory. This group is mandatory. You know, sp2 hybridized carbon means carbocation sp2 carbon, carbon radical sp2 carbon. Okay, and double bonded carbon, alkene, double bonded carbon is sp2 carbon. This is the reason this hyperconjugation concept can explain the stability of carbocation, carbon radical, and alkene stability. I hope everyone understood. This is the reason this hyperconjugation concept can explain the stability of carbocation, carbon radical, alkene carbon. So very important. This concept can explain the stability of carbocation, carbon radical, alkene or alkenes. So this concept can explain the stability of carbocation, carbon radical, alkenes. Example: ethyl carbocation ethyl carbocation CH3 CH2 plus ethyl carbocation. You know, carbocation is sp2 hybridized carbon. Adjacent carbon CH3, that is sp3 carbon, that is known as alpha carbon. Okay, so for hyperconjugation sp3 carbon is mandatory, alpha carbon is mandatory. sp2 carbon just adjacent carbon, if it is sp3 carbon, that is alpha carbon. Understood? Now this is sp2 carbon. Why it is sp2 carbon? Here carbocation connected to carbon-carbon sigma bond and two hydrogens, two sigma bonds, three sigma bonds. Three sigma bonds means sp2 hybridization. Three sigma bonds means 6 electrons, less than 8, deficient. Now adjacent carbon is no doubt purely 4 sigma bonds, sp3 carbon. Can we say it is alpha? No doubt at all, it is alpha. So sp2 carbon adjacent carbon is sp3 carbon, no doubt it is alpha carbon, simply. Now sp2 carbon, that is deficient carbon. That's why adjacent CH sigma bonded electrons involved in resonancy. Now here CH sigma bonded electrons involved in pi bond formation, involved in stabilization of carbocation. Now here double bond existed. Now once observe this carbon, around this carbon how many bonds are there? Double bond, sigma bond, sigma bond. So total 4 bonds. 4 bonds means 8 electrons. Octet satisfied, stabilized. Simply it is stabilized. Is it right or not? CH sigma bonded electrons can be stabilized adjacent carbocation. This is main concept. So now how many alpha hydrogens are there? 3. Already one hydrogen participated. Now for the second hydrogen you can write another hyperconjugated structure. Another hyperconjugated structure. Now with the third alpha hydrogen, you can write third hyperconjugated structure. Understood or not? So 1, 2, 3. You can clearly observe these 3 structures are no bond resonancy structures. Clear? These 3 structures are called no bond resonancy structures because in between carbon and hydrogen there is no bond. That's why simply they are called no bond resonancy forms or hyperconjugated structures. Understood or not? So these are hyperconjugated structures. Understood? How many hyperconjugated structures? 3 hyperconjugated structures. How many hyperconjugated structures? 3 hyperconjugated structures. Then the starting material can we add or not? Yes. That's why very simple, resonancy forms is equal to 3 hyperconjugated structures plus this starting material. That's why what is the formula? Resonancy forms. Total resonancy forms is equal to number of hyperconjugated structures plus 1. Number of hyperconjugated structures, they are formed based on number of alpha hydrogens. Simply number of resonancy forms is equal to number of alpha hydrogens plus 1. Clear? Here 3 alpha hydrogens, so resonancy forms 3 plus 1, 4. I hope everyone understood. Clear? Yes. So now we can write what is the formula? What is the formula? Total resonancy forms is equal to number of alpha hydrogens plus 1. Number of alpha hydrogens plus 1. This is very important formula. This is very important formula. Understood? Total resonancy forms is equal to number of alpha hydrogens plus 1. Clear everyone? So very important concept. Similarly, we can explain stability of carbon radical. Similarly, we can explain stability of alkene. Understood or not? Yes. So now carbon radical stability also we can explain like. Now stability order. Stability order of carbocation. Now tertiary butyl carbocation. Tertiary butyl carbocation greater than isopropyl carbocation, greater than ethyl carbocation, greater than methyl carbocation. Understood? Methyl carbocation. This is stability order. Now how many alpha hydrogens are there? 9 alpha hydrogens. So 9 hyperconjugated structures. How many alpha hydrogens are there? sp2 adjacent carbon, sp3. They are called alpha carbons, alpha hydrogens. Clear? So now 6 hyperconjugated structures. Now only 1 alpha carbon, 3 alpha hydrogens, 3 hyperconjugated structures. Here no alpha carbon, no sp3 carbon. That's why 0 hyperconjugated structures. Now resonancy forms we can write 10 resonancy forms, 7 resonancy forms, 4 resonancy forms. So methyl carbocation resonancy forms 0. It is not involved in resonancy. Clear everyone? So this is the stability order. Understood? This is the stability order. So tertiary carbocation greater than secondary carbocation greater than primary carbocation greater than methyl carbocation. Clear? Similarly, carbon radical stability also we can explain. Same order. Tertiary carbon radical which is greater than secondary carbon radical which is greater than ethyl carbon radical greater than methyl carbon radical. Understood? So now next example. Moving to next page. So now next example. Alkene stability. Alkene, for example, propane. CH3, CH double bond, CH2. sp2 double bond carbon, adjacent carbon sp3 carbon. Yes, it is alpha. How many alpha hydrogens are there? How many sp3 hybridized hydrogens are there? 3. So that's why 3 hyperconjugated structures. Now this is alpha, this is sp3, this is sp2. So now this CH sigma bonded electrons involved in hyperconjugation. Now we can write this CH sigma bonded electrons involved in hyperconjugation Now second hydrogen, if it is participated in hyperconjugation, then this resonance structure is formed. If third alpha hydrogen, if third alpha hydrogen third alpha hydrogen third alpha hydrogen, if it is participated in hyperconjugation, this structure is formed. Understood, everyone? So these three are called hyperconjugated structures. So three hyperconjugated structures are formed. Three no bond resonancy structures are formed. There is no bond in between carbon and hydrogen during the resonancy. That's why they are called no bond resonancy forms. Clear? And we can add these starting material also. That's why total resonancy forms is equal to number of alpha hydrogens plus 1. Same formula. Okay? Total resonancy forms is equal to number of alpha hydrogens plus 1. Resonancy forms 4. Hyperconjugated structures 3. Clear, everyone? Now, stability order. Stability order of alkenes. Stability order of alkenes. Stability order of alkenes. You know, this is tetrasubstituted alkene. It is tetrasubstituted alkene. Tetrasubstituted alkene. You know, this is sp2 carbon. sp2 carbon. Just adjacent carbon is sp3 carbon. Just adjacent carbon is sp3 carbon. sp3 carbon. Now, how many alpha carbons are there? 4. How many alpha hydrogens are there? 12. So 12 hyperconjugated structures. Now coming to next structure. Next structure. Trisubstituted alkene. Trisubstituted alkene. Now this is alpha. This is alpha. This is alpha. Now 9 hyperconjugated structures. 9 alpha hydrogens. Now disubstituted alkene, but trans. It is trans. So trans disubstituted alkene. Trans disubstituted alkene. How many alpha hydrogens? 6. 6 hyperconjugated structures. 6 hyperconjugated structures. Clear? Now coming to another disubstituted alkene. This is more stable. This disubstituted alkene is more stable. 2 methyl groups connected to same sp2 carbon. Same sp2 carbon. So this is also disubstituted alkene. Okay, disubstituted alkene. 6 hyperconjugated structures. Actually, it is not participated. This structure not participated in geometrical isomerism. It is not involved in geometrical isomerism because same double bonded carbon having 2 identical methyl groups. It is not involved in geometrical isomerism, but it is stable as compared to cis. As compared to cis disubstituted alkene, this alkene more stable. You will learn in upcoming lectures. This concept I will explain in upcoming lectures. Next one, cis disubstituted alkene. Cis means two alkyl groups, identical alkyl groups are on same side of the double bond. It is cis. Cis disubstituted alkene. Cis disubstituted alkene. Here also 6 alpha hydrogen, 6 hyperconjugated structures. Next to monosubstituted alkene. Monosubstituted alkene. Already I have explained this one as an example. Already explained. You know, this is simply monosubstituted alkene propene. It is monosubstituted alkene. Only 3 alpha hydrogens, 3 hyperconjugated structures. Last one, simple alkene, ethylene. Here no sp3 carbon. This is the reason it is not involved in hyperconjugation. So 0 hyperconjugated structures, no sp3 carbon, no alpha hydrogens, no hyperconjugation. Understood? This is very important order, stability order. So stability of alkenes also explained by hyperconjugation. Clear? We can explain the stability of carbocation, carbon radical, alkene stability. Carbocation stability order, carbon radical stability order same. That's why I didn't explain carbon radical stability order. I hope everyone understood this one. Next one, applications. Applications. So important concept, applications. Bridgehead alpha hydrogen. Bridgehead alpha hydrogen is not involved in hyperconjugation. Very important point. Bridgehead alpha hydrogen not involved in hyperconjugation due to steric repulsive forces. Example, this is carbocation. Okay, this is carbocation. Here carbocation, adjacent carbon is alpha carbon, just adjacent carbon is alpha carbon. Now due to angle strain, this bridged alpha hydrogen move away from the plane, due to angle strain. Understood? So now this hydrogen is out of the plane. That's why even though it is sp3 carbon, even though it is alpha hydrogen, but it is bridged alpha hydrogen, Due to steric repulsive forces, that hydrogen move away from the plane. That's why this CH sigma bonded electrons cannot stabilize the carbocation. That's why this bridged alpha hydrogen not involved in hyperconjugation. What is this? This is bridged alpha hydrogen. It is not involved in hyperconjugation. But other side alpha carbon is there now. Those hydrogens are involved. Okay, those hydrogens are involved. Understood? That's why finally overall molecule, finally this molecule involved in hyperconjugation due to presence of these hydrogen atoms. So it can participate in hyperconjugation. I hope everyone understood. Now coming to another example. Another example, this bridged alpha hydrogen not involved, no doubt at all. Now this is also adjacent carbon, alpha carbon, but no alpha hydrogens. Okay, no alpha hydrogens, no alpha hydrogen. That's why it is not involved in hyperconjugation. It is not involved in hyperconjugation. I hope everyone understood this one. Very, very important application. Very, very important application. So in first example, alpha hydrogens are there, other side, so participated in hyperconjugation. But second example, bridged not participated, of course, and other side alpha carbon is there. At that carbon, no alpha hydrogens, phenyl groups, benzene rings are there. That's why overall molecule not involved. Clear? Now coming to next application. Now here also I am giving two examples which is participated in hyperconjugation, which is not. Here first example, of course carbocation connected to again sp2 carbon. This side also sp2 carbon. But this carbocation conjugated with left side double bond and right side double bond also. Now where conjugation is ending, that ending carbon is attached to sp3 carbon, both side. Okay, so now at this sp3 carbon also we can call alpha carbon. Understood? This is the reason these hydrogens also involved in hyperconjugation. These hydrogens are also involved in hyperconjugation. Understood everyone? Where conjugation is ending, that ending sp2 carbon attached to at least one sp3 carbon. At that carbon at least one alpha hydrogen is there, that is also participated in hyperconjugation. Very, very important application. It is also very, very important application. But in second example, that cation conjugated with double bonds, but here sp3 carbon is there, that is alpha carbon, sp3 carbon is there, but at which carbon? No hydrogens. So that's why it is not participate, it is not involved in hyperconjugation. But first example, it can participate participate in hyperconjugation. First one involved, second one not involved. Now moving to next page. Now next example. All are of course similar examples but very important. Now this molecule, is it participate in hyperconjugation? Simply no. Why? Simply no sp3 carbon. No sp3 carbon. It is sp2, 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 sp2. This is also sp2, sp2. Simply no sp3 carbon. So not involved in hyperconjugation. Not involved in hyperconjugation. Now next application. Yes. Is it involved in hyperconjugation? And its name is allylic carbocation. Allylic carbocation. Is it involved in hyperconjugation? Simply no. Why? Carbocation sp2. This is sp2. This is sp2. Finally, no sp3 carbon. So that not involved in hyperconjugation, but it is involved in resonancy, allylic carbocation, but purely it is not involved in hyperconjugation. Now next one. So is it involved in hyperconjugation? Yes, 100%. Carbocation conjugated with this double bond. This double bond directly connected with one sp3 carbon. At that sp3 carbon, one alpha carbon is there, alpha hydrogen is there. So that sp3 carbon is alpha carbon. Yes, 3 alpha hydrogens are there. Okay. Carbocation conjugated with one double bond. That double bond carbon sp2 carbon directly attached to one sp3 carbon. That sp3 carbon is called alpha carbon. At that carbon, 3 alpha hydrogens are there. That's why here 3 alpha hydrogens involved in hyperconjugation. Like, okay, so 3 alpha hydrogens can stabilize the carbocation. So it participate in hyperconjugation. It participate in hyperconjugation. Understood? Now one simple question. How many hyperconjugated structures possible for below molecule? Below molecule. How many hyperconjugated structures possible for below molecule? How many hyperconjugated structures possible for below molecule? So what is the answer? How many hyperconjugated structures possible for below molecule? Carbocation just adjacent carbon is sp3 carbon, that is alpha. Alpha, alpha, alpha. So now here one hydrogen is there. Here 2 hydrogens are there. Here also how many hydrogens are there? 2 hydrogens. Total how many alpha hydrogens? 5. So 5 alpha hydrogens. That's why 5 hyperconjugated structures. What is the answer? 5 hyperconjugated structures. 5 alpha hydrogens, so that's why 5 hyperconjugated structure. Just carbocation adjacent carbon, if it is sp3 carbon, simply that is alpha carbon. Understood? So this is very important concept. So I explained bridged alpha hydrogen, that is not involved in hyperconjugation. Bridged alpha hydrogen, that is not involved in hyperconjugation. Understood? So this is very important concept. Very important concept. Okay. Thank you.